In this video, we will be looking at section 8.4, which covers vectors. A vector is an object that has both a length and a direction. A vector can be represented by an arrow that has a fixed length and indicates a direction. We represent vectors a few different ways. If we have 2 points we're working with, we'll say the first point and then the second point and write an arrow over them saying we're going from point A to point B. We could use just a single letter to represent a vector. We can either bold it or write an arrow over the top of it. Typically, we'll use the arrow notation just because we're handwriting things and we can't really bold our handwriting. So we're going to start by drawing a vector v that travels from the origin to 2, -3. So let's find 2, -3. And we're going to draw an arrow from the origin to that point. And that is our vector v. That's all there is to it. Next up, we're going to draw a vector u that travels from -5, 4, so let's find that, to 2, 1. That'll be here. Once we connect the dots, make sure you start in the right place because the direction of the arrow matters. It'll look something like that, assuming I can draw a straight line, and that represents vector u. We are actually able to add, subtract, and multiply vectors, which is pretty cool. We're going to start by adding them geometrically. To add vectors geometrically, draw v starting from the end of u. Then the sum u plus v is the vector from the beginning of u to the end of v. And hopefully this will make a little bit more sense once we have an example. So given u and v below, we're going to draw the sum u plus v. So what I'm going to do is I'm going to take this vector v and move it so it starts at the end of u. So it's going to look something like, oh, that's not quite the right angle. Something like that is going to be our vector v. And then u plus v starts at the beginning of u and goes to the end of v. So this vector in blue is u plus v. So you just pick up the second one and move it so it starts at the end of the first one. And then to create the sum of them, start at the beginning of the first, go to the end of the second. Next, we're going to talk about how we multiply, which is called scaling vectors. To geometrically scale a vector by a constant, scale the length of the vector by the constant. So the direction stays the same, but the length is what gets multiplied. However, if we scale a vector by a negative, it will reverse the direction of the vector. So hopefully that'll make a little bit more sense once we have an example for that as well. So this is a vector u. First we want to draw 3u. So it will be in the same angle as u, but it'll be 3 times as long. That's got to be pretty close. So that will be 3u. Negative u is going to take u itself, but just go in the opposite direction. So we take u and point it in the opposite direction. That will be negative u. And as you can probably imagine, negative 4u will be just like the vector u, negative u, but 4 times as long. I'm just guessing here, but use your best judgment. You'll be doing these online, so it'll have a little bit better concept of how long these things should be. This idea of negative vectors is going to help us subtract them. So if we're given u and v below, we're going to draw u minus v. Now before we actually do that, I want to talk about what u minus v actually means. When you first learned subtraction, it's quite, okay, maybe not when you first learned subtraction, but a little ways down the road, you probably learned that 2 minus 4 was equal to 2 plus a negative 4. We're going to use that idea here. U minus V is going to be equal to U plus a negative V. So first up, let's see what negative V is going to look like. So if this is V, the negative V is going to look something like that. I want to take U plus my negative V. So I'm going to take my negative V and attach it to the end here. And then to add them, you start at the beginning of the first and go to the end of the second. And that's going to be our U minus V. Next up, we're going to talk about some definitions here. First, we have magnitude. So that's going to be the length of your vector. We represent it either by making it look like absolute value or double absolute value. So you'll see these vertical lines around the vector. That represents the magnitude or the length of it. And then a unit vector, kind of like the unit circle, how that's a circle with a radius of 1, a unit vector is going to be a vector with a length of 1. This is going to help us work with vectors algebraically. So component form. A component form of a vector represents the vector using two components, x comma y, but you'll notice they're in these angle brackets, and they indicate the vector as a displacement of x units horizontally and y units vertically. So how you get from the start to the end, you're moving x units horizontally and y units vertically. Conveniently, this makes a right triangle. So the magnitude of the vector is the length of the hypotenuse of this right triangle. So we can use the Pythagorean theorem and we get x squared plus y squared equals the magnitude squared, which is just like x squared plus y squared equals r squared that we used in polar form. There's one more notation I want to run by you guys so that you have it kind of in your mind. Sometimes you may see vectors written as a combination of unit vectors I and j, where I points to the right and j points up. In other words, the unit vector I goes 1 in the x direction and 0 in the y direction, so it's just 1 unit to the right. And j is going to be our vertical unit vector. It points straight up and it has a length of 1. So this I is not the same as the imaginary number I because it has an arrow over it, so it's a vector. That's what makes it a little bit different. So if we are using this notation, we could write the vector u, if it is angle bracket 3 comma negative 4, we could write that as 3i minus 4j, because we are moving 3 in the x direction, which is 3 of these. And then we're going down 4. So we need to take this and flip it over, which makes it a negative j, but we want a length of 4, and that's what makes it become minus 4j. So now we're going to see if we can work with these vectors a little bit. So first up, a vector with magnitude 5 points in a direction 75 degrees counterclockwise from the positive x-axis. Find the components of this vector. So I'm just going to start by making a very crude sketch. So if that is our Cartesian plane, this is going 75 degrees counterclockwise from positive x-axis. So that's going to be this way. We know this angle is 75 degrees, and then the length is 5. If I drop a little dotted line here, I'm going to zoom in, make sure we can really see what's going on. If I drop straight down to the x-axis, you might see that I have a right triangle I'm working with here, where we know this angle is 75 degrees and the length is 5. We need to find the x component and the y component. Well, if it's a right triangle, we can use our trig functions. For x, we're going to have to use cosine because that's the adjacent and the hypotenuse. So the cosine of 75 degrees is equal to x over 5. And that means x is equal to 5 times the cosine of 75 degrees. I can type that in the calculator, that's all fine and dandy, I'm going to, but I want you to remember that we also have the formula x is equal to r cosine of theta. Bam, it's right there. This is why that's true. All right, I already made sure that my calculator is in degree mode, so let's do 5 cosine of 75. We get that the x component is 1.2941. And then as you can imagine, y is going to be equal to 5 times the sine of 75 degrees, which gives us 4.8296. So if we wanted to write this in component form, we could write it as angle bracket 1.2941, comma 4.8296. Close the bracket. Next up, we're going to find the components, the magnitude and angle theta of the vector that travels from the origin to the point 3, 5. I'm going to start with a drawing again because I think that helps a little bit. We are going from the origin to the point 3, 5. 3, 5 is in the first quadrant. So that's our vector. Dropping this down, we know that the x value is 3, and the y value is 5. First up, we want to find the components. Well, that's just the 3 and the 5. Because we started at the origin, we know we traveled 3 to the right and 5 up, and that's how we get our components. The magnitude is the length of the vector. Well, it creates a right triangle, so we can use the Pythagorean theorem. 3 squared plus 5 squared is equal to our magnitude squared. I'll call this u. So we'll say the magnitude of u squared. 3 squared is 9, 5 squared is 25. Adding those together, we get the magnitude of u squared. So that means 34 is equal to the magnitude of u squared. And thus the magnitude of u is the positive square root of 34. Finally, we need the angle theta of the vector. It's going to be that angle there. We know the opposite and the adjacent, so that sounds like tangent to me. The tangent of our angle theta is equal to the opposite 5 over the adjacent 3. So to solve for theta, I can inverse tangent. The inverse tangent of 5/3 gives me that theta is equal to 59.0362 degrees. Next up, we're going to work on combining vectors algebraically. So we did it geometrically earlier. Now we're going to use this component form. So to add, subtract, or scale vectors in component form, we'll start by being given a vector u that has components u1 and u2, vector v that has components v1 and v2, and c is going to be any constant. If we want to add the two vectors together, we just add the corresponding components. So u plus v is equal to u1 plus v1, u2 plus v2. If we want to subtract them, we subtract corresponding components. So u1 minus v1, u2 minus v2. And then if we want to scale a vector, we scale each of the components. So if we want to take a vector u and scale it by c, we'll have cu1, comma cu2. This is going to allow us to do arithmetic with our vectors. So given u, which is equal to -3, 4, and v, which is equal to -2, 1. We want to find u plus v, u minus v, and 2u minus 3v. So first up, we have u plus v. I'll have -3 plus -2, comma 4 plus 1. That gives me -5, +5. And that's all we do to add them. For subtraction, I'll have -3 minus -2, comma 4 minus 1. That will give me -1, comma 3. Finally, we have 2u minus 3v. I'm going to take this kind of step by step so I don't miss anything. I'm going to start by finding 2u and 3v, and then I'll subtract them. So 2u, I take 2 and multiply it by each of the components. So 2 times -3 is -6, 2 times 4 is 8. And then for v, I'm multiplying them by 3, so I get -6, comma 3. So now I'm going to subtract them. 2u minus 3v is equal to, I have -6 minus a -6, comma 8 minus 3, which gives me 0, comma 5. Now this idea here at the end, the arithmetic with vectors in component form, this is going to be really useful as we look at some of these application problems. First up, a person starts walking home and walks 4 miles east, 2 miles southeast, 5 miles south, 4 miles southwest, and 2 miles east. How far have they walked? If they walked straight home, how far would they have to walk? And in what direction would they need to walk? There's a lot going on with this problem, but let's start with the first question because I bet you can do that. We want to know, how far have they walked? Well, first they walked 4 miles, and then 2 miles, 5 miles, 4 miles, and 2 miles, 4, 5, 6, 11, 15, 17. So they've walked a total of 17 miles. Now for the rest of this, we are looking at them at their final spot, trying to go back home. So I'm going to try to draw a picture of what's going on here. We have to be careful with our directions, make sure we don't miss anything there. So looking at directions, up is north, right is east, down is south, left is west. So first they go 4 miles east. So if we start here, we can go 4 miles this way. And then 2 miles southeast. So southeast is going to be between south and east. We're only going to go 2 miles that way. Then we're going to go 5 miles south. 4 miles southwest. And then 2 miles east. It'll look something like that. We want to know if they walked straight home, how far would they have to walk? And that's going to be this distance here. I'm just going to put a little arrow on it. The way I thought of this was by taking each step and writing it as a vector. So let's see. First, this person walked 4 miles east. If I put this in vector form, that means they went 4 to the right and 0 up or down. Then they went 2 miles southeast. That one's not entirely clear right away what the components are. So if they went 2 miles southeast, We have 2 for that direction. We need to know the x, because I put that 2 on the wrong side, and the y value there. But if it was truly southeast, this is 45 degrees here. So we have our x and our y. We know this angle, so the adjacent is x, which is going to be cosine. We get that the cosine of 45 degrees is equal to our x over 2. Multiplying over, we get 2 times the cosine of 45 degrees is equal to x. We know the cosine of 45 degrees is square root of 2 over 2. That leaves us with the square root of 2 for x. If we set up our triangle to solve for y, we will have the sine of 45 degrees is equal to y over 2. That gives us 2 times the sine of 45 degrees is equal to our y value. The sine of 45 degrees is square root of 2 over 2. And that gives us square root of 2 again for y. Just be careful. I drew this in a way to where x needs to be positive and y needs to be negative. So our x value is positive square root of 2 and our y value is negative square root of 2. Then we go 5 miles south. That has components 0, -5. Then we go 4 miles southwest. So southwest is going to be down and to the left. We need an x and a y coordinate. It's still 45 degrees. So this time we went 4 miles. We need an x and a y. We get that the cosine of 45 degrees is equal to x over 4. So x is 4 times the cosine of 45 degrees, which is 4 times the square root of 2 over 2, which is 2 times the square root of 2. Solving for y, we'll have the sine of 45 degrees is equal to y over 4. So y is equal to 4 times the sine of 45 degrees. So that will be 4 times square root of 2 over 2, which is 2 square root of 2. This time x is negative and y is negative. So this is going to be negative 2 root 2, comma negative 2 root 2. And finally, they went 2 miles east, which is 2, 0. So if we want to figure out how to get from where they started to where they ended, I can add all of these up. So I'm going to start with my x components. We have 4 plus the square root of 2 plus 0 minus 2 square root 2, and then plus 2. So our x coordinate is 4.5858. Our y coordinate is going to be 0 minus square root of 2 minus 5 minus, 2 square root of 2. Whoops, too many parentheses. We get a y coordinate of negative 9.2426. So if this person went directly from home to this point, this is how they'd have to get there. So to get home, we just have to go in the opposite direction. So that would mean to get home, we have to go negative 4.5858 for our x direction and positive 9.2426 for our y direction. And hopefully that makes sense because we have to go to the left, which is west, and north, which is up, to get home. So we already answered how far they've walked total. That was the 17 miles. Now we need to know if they walked straight home, how far would they have to walk? Well, we know it's this much in the x direction and this much in the y direction. So we can use x squared plus y squared equals r squared, or the magnitude of a vector squared, however you want to think of it. I'm going to use r squared because that's just easier to write. So we'll have negative 4.5858 squared plus 9.2426 squared is equal to r squared. So negative 4.5858 squared plus 9.2426 squared equals, and square root that answer to get that r equals 10.3177. So currently they are 10.3177 miles from home if they can go straight there. Well, now we need to know what direction do we have to go to get there. Well, we know we have this kind of sort of triangle going on. If this direction is north, that doesn't even look like an N. We know we have to go 9.2426 miles this way and 4.5858 miles that way. If I find this angle, that should help me solve it. I know the opposite and the adjacent. So the tangent of my angle that I'll call theta is equal to 4.5858 over 9.2426. And if I inverse tangent that, I get that theta is equal to 26.3887 degrees. What that measures is how much we need to turn west from north. So we would say that this person needs to walk 26.3887 degrees west of north. So start by facing north, turn 26.3887 degrees west, walk for 10.3177 miles, and they should make it home just fine. With rounding issues and variability, but hey, we're not going there. Next up, an airplane is heading north at an airspeed of 600 kilometers per hour, but there is a wind blowing from the southwest at 80 kilometers per hour. How many degrees off course will the plane end up flying, and what is the plane's speed relative to the ground? Okay, so the airplane is heading north. That's the way it's flying all by itself. At an airspeed of 600 kilometers per hour. So there's a wind blowing from the southwest. So from the southwest towards the northeast, then it's pushing the plane this way at 80 kilometers per hour. So what that means is the plane is actually going this way, which should make sense because that wind is pushing the plane east a little bit. We want to know how many degrees off course the plane ends up flying. So that's going to be that angle measured. And the plane speed relative to the ground, well, if this is a speed, this is a speed, this is going to be a speed. So we'll use r for relative to the ground, I guess. I'm just making stuff up at this point for variables. Okay, whatever works. So now we need another piece of information because it looks like we don't have enough here. Because I don't have a right triangle, I can't use the Pythagorean theorem. But based on everything else, I might be able to use a law of sines or a law of cosines. So let's see if there's anything else I know here. The wind is blowing from the southwest. If I draw in my northeast, south, and west, it's blowing from the southwest towards the northeast. This angle right here is 45 degrees. But this angle down here is 90 degrees. That means if I redraw this whole triangle, forgive me for drawing poorly, we get 135 degrees here. This is 80. This is 600. That's the angle I'm solving for, and that's R. This is a side angle side case, and I should be able to use the law of cosines on it. So I will have R squared is equal to 600 squared plus 80 squared minus 2 times 600 times 80 times the cosine of the included angle, 135 degrees. That can all go straight into my calculator. 600 squared plus 80 squared minus 2 times 600 times 80 times the cosine of 135. Remember, that's R squared, so if I square root that, I get that R is equal to 659.0009. Cool thing is, R is one of the things I was trying to find. That's the plane speed relative to the ground, and we were measuring speed in kilometers per hour. Well, that still doesn't solve my problem of how far we are at an angle. But now that I have this distance R, the speed R as 659.0009, now I can use the law of sines. Because I have the angle 135 and its opposite side, so the sine of 135 degrees over this answer I just got is equal to the sine of my angle that I'm trying to find over its opposite side, 80. If I multiply both sides by 80, I get the sine of theta is equal to 80 times the sine of 135 degrees over 659.0009. So if I take the inverse sine of that, I should get my angle. Inverse sine of 80 sine of 135 divided by 659.0009 looks like our theta is 4.9243 degrees. So the plane is going to be going 4.9243 degrees off course. We're going to keep thinking about planes, but in a way that may seem more practical. An airplane needs to head due north, but there is a wind blowing from the northwest at 80 kilometers per hour. The plane flies with an airspeed of 500 kilometers per hour. To end up flying due north, and that should be DUE, sorry, the pilot will need to fly the plane how many degrees west of north? All right, let's see if we can visualize what's going on here. There's a wind blowing from the northwest. If it's coming from the northwest, then it is pushing towards the southeast, and that's at 80 kilometers per hour. The plane is trying to go due north. That's how it wants to end up. So we need to figure out what does it need to do in the meantime to end up going that path. And we know it's flying at 500 kilometers per hour. Well, kind of like last time, we have a 90-degree angle and a 45-degree angle. So this whole thing is 135 degrees. So let's see if we can figure out what we're trying to find before we start finding stuff that might not be helpful. We are trying to figure out how far the pilot needs to go in degrees west of north. So due north would put us on this track. We need to figure out what this angle is. But if purple is due north and black is due north, then that angle should be the same as this angle. They're called alternate interior angles because this is how far the plane would have to turn west if it's going north. If it were going the other way, it'd be kind of the opposite angle. I don't know how to describe it, but it's true. If we find this angle, it will be the same as the angle we're trying to find. Well, since I have an angle and its opposite side, I might be able to use the law of sines here. The sine of 135 degrees over 500, which is the plane's speed, is equal to the sine of this angle I'm looking for over 80. If I multiply both sides by 80, then I get the sine of theta is equal to 80 sine of 135 degrees over 500. And let's type that in. The inverse sine of 80 sine of 135 divided by 500 tells me theta is equal to 6.4962 degrees. So if this plane goes 6.4962 degrees west of north, then they will be headed due north when you factor in the wind. All right, there's just one question left, and I tried to make it one that wouldn't seem quite so stressful. Two children are throwing a ball back and forth straight across the back seat of a car. The ball is being thrown at 8 miles per hour relative to the car, and the car is traveling 45 miles per hour down the road. If the child doesn't catch the ball and it flies out the window, in what direction does the ball fly? All right, so this is kind of what I'm picturing. We have a car, beautiful car, I know. It's going down the road at 45 miles per hour. Then the kids in the back seat are throwing a ball back and forth at 8 miles per hour, and it's going to go that way. It could go either way, but I'm going to pick that way. So if we put these two forces together, we get 45 miles per hour, and then I want to add the 8 miles per hour that's going this way. We need to figure out what angle it's going to travel. This is actually a right triangle because we have north and, I guess in the way I drew it, east. I have the opposite and the adjacent. This is just a tangent problem. The tangent of my angle is equal to 8 over 45. If I inverse tangent it, I get that theta is equal to 10.0806 degrees, and that's all it wants. This ball is going to fly at an angle of 10.0806 degrees. That is the end of pre-calculus.